Welcome to another LabVolt tutorial about the 8960. This video will introduce you to a function included in the 8968-20 function called 4-quadrant constant speed prime mover brake. To gain access to this function, make sure that your 8960-20 is equipped with the option 8968-20, which allows you to connect your module to LVDAC EMS for remote control. Proceed by selecting dynamometer on the front panel of the 8960, then connect the 8960 to your computer using a USB cable, and then start LVDAC EMS. Once it is fully opened, click on this icon to open the 4-quadrant dynamometer power supply window and select 4-quadrant constant speed prime mover brake in the function selection list. Now let's take a look at the settings of this function. Speed control. Select knob or 8960 command input to decide which of the two will control the speed of the motor. Speed sets the speed of the prime mover. This function allows the user to control the speed from -2500 RPM to 2500 RPM, which means that the prime mover can go clockwise and counterclockwise without changing any settings or functions. Pulley ratio sets the ratio between the pulley on the prime mover and the one on the machine under test. For accurate measurement, always verify this ratio to be sure the right one is selected. The value represents the number of notches on each pulley. Thermistor type. Choose your thermistor type function based on what you want to protect. Type 1 is for nickel metal hydride batteries, and Type 2 is for the LabVolt motor. Status indicates if the function is started or not. Here are the meters showing the parameters at the shaft of the machine under test, the single refresh and automatic refresh button, the knob, and finally, the start-stop button to control the function. You can also find here a graph explaining the function. By looking at this graph, you can see that this function is able to work within the 4-quadrant of a couple versus speed diagram. In this demonstration, I will use an induction motor to demonstrate the 4-quadrant operation of the 8960. To do so, I have connected the induction motor to the power grid and coupled its pulley with the one on the prime mover using a belt. Depending on which quadrant the prime mover will be, electrical power will be supplied to the prime mover or created by the prime mover to get back into the power grid through the power cable. Using the data table, I'll record every parameter of these meters for each quadrant. Let's get started. First, I start my induction motor using a power supply connected to the power grid. Since my power grid is at 60 Hz, I can expect the induction motor to speed up to 1780 RPM. So I set the prime mover to a constant speed of 1780 RPM and start the function. Now this point is the neutral point between quadrant 1 and quadrant 4. I save these values using the data table. Now let's decrease the speed of the prime mover to 1720 RPM. As you can see here, the power generated is positive, which means that the induction machine is now a motor that supplies mechanical power to the prime mover, which converts it to electrical power and sends it back to the power grid through the power cable of the 8960. Positive speed and positive torque show that we currently are in the first quadrant here. Let's save these values and speed up the prime mover to 1840 RPM. At this speed, the power is now negative, which means that the induction machine is now a generator, converting mechanical power to electrical power and sending it back to the power grid. Positive speed but negative torque means that we are operating in the 4th quadrant. Again, I save the data using the data table. Now I stop the function and reverse the direction of rotation of my induction machine so that it will turn counterclockwise. The new speed is now close to -1780 RPM. I can then set the prime mover constant speed to -1780 RPM using this function and then start the function. We are now at the neutral point between quadrant 2 and quadrant 3. Let's save those values. As I decrease the speed to -1720 RPM, you can see that the power is positive again. The induction machine is now a motor, rotating counterclockwise, which implies that the prime mover is generating electrical power and is sending it directly into the power grid. Negative speed and negative torque proves that we are now operating in the 3rd quadrant. After saving these values, I speed up the prime mover to negative 1840 RPM. At that speed, the power is negative, which means that the induction machine is now a generator, sending electrical power back to the power grid. Negative speed associated with positive torque proves that we are currently operating in the second quadrant here. After saving the last data, I can check my table to see if I really experienced every single quadrant operation by verifying the speed and torque combinations. You can also see here the 2 neutral points recorded. That's how the 4-quadrant constant speed prime mover brake works.